not quite good. Okay, anyway, so today we have first two lectures of mini course by Viktor Tchoulaevski, and he will talk about multi-particle Anderson localization.
Yeah, again, what about the good point for making a break? Unless everyone...
We definitely should make a break.
Okay, then you decide.
Yes.
Okay. Okay. Well, thank you. Well, many years ago, in the Moscow University, Israel Moisevich Gelfand used to explain, or used to say that one cannot discuss or explain something which is not written on the blackboard. So let's me present you the main character for this story. I'm going to tell you a multi-particle Hamiltonian, or let's say Hamiltonian for an interacting particle system, since we have been discussing this on other occasions. What is a multi-particle? What is many particle? Anyway, it is a system with interaction, with non-trivial interaction, that's for sure. Okay, so one way to write in a short way is to say that there is a kinetic energy of the entire system, and there are n particles. Okay. Now, the particles, for example, live each in a d-dimensional lattice. It may be some more, there shouldn't be n superscript n here, just x lives in something, configuration space of single particle system, or physical configuration space, and it may be z to the power d. So n is to be removed here. Now, in more detailed way, we can say that we take first n replicas of single particle Hamiltonians, okay, each acting on its own quantum particle with position xj, okay, and unless we have u of x, an interaction, we can use separation of variables, and there is no reason to make any talk about it. It would
Xj is in Zt. Xj is in Zt.
Yes, as an example. It may be a more general lattice.
So fat x is then in Zt to the n. Correct.
Oh, sorry. Then, okay, you are correct. This is a boldface x, and this means that z, script z, has to be raised to the power. Okay, the other way around. Okay, so like I said, these are replicas. Oh, have long battery? No. And what about the random potential? Well, as to interaction, it has.
You look at Fermi or boson?
I will say that. Okay, just a moment. Neither. Okay, one can take either, but I will speak of neither of them. Now, the interaction may have usual two-body structure. It doesn't have to have such a structure for the methods that can be applied in this framework, but the physically most relevant is this case. And is U two-body interaction short range, long range, rapidly decaying, slowly decaying? It's a matter of choosing a particular model. Now, the random potential, since we started with replicas of initially independent particles, random potential, the total potential energy, which is not due to interaction, but comes from the exterior point, from the, let's say, infinitely heavy crystalline structure, from ions surrounding the electrons. It's just sum of the individual potential energies for each particle, and that's it. Of course, one has to make a model specific to choose this random field, and indeed this is a random field on Z, whatever be the nature of the set Z, relative to some probability space, which I denote by omega, which is a real value. And of course, one can take one or another hypothesis about the nature of the field. Okay, we are going to discuss a model a particular but important model where this V is ID, but it has identically distributed independent values at each side. Okay, so we are speaking about. Well, today we are going to speak only about discrete configuration spaces. In the second half, in a week, I will cover briefly another approach based on the fractional moment method, which was discussed already in this room a few weeks ago. And also, I will say a few words about the continuous models in continuous configuration spaces, such as RD or quantum graphs. Both are acceptable here, and both have been treated in one or another way. Okay. Now, the simplest case for one of the most important ingredients of the scalar analysis for eigenvalue concentration estimates. The simplest case is where this random field, and we agreed to have it ID, has a probability distribution function which is Lipschitz or Hölder continuous. Well, actually, any order of Hölder continuity goes smoothly. Both for the approach I'm going to discuss today, multi-particle version of multi-scale analysis, and for the multi-particle variant developed by Eismann and Warzel of the fractional moment. Both can work with Hölder continuous single-site distributions of an IID field. Multi-scale analysis is known to be less exigent as to the regularity of single-site potential. It can work even with log Hölder continuous distributions. Okay, let me see. Yeah, okay. Now, a few references. Well, let me say first what this talk is not, well, this mini course is not going to be. This is not going to be, well, a presentation of a 3-page hypothesis and 50 pages of proof of one large, heavy, boring theory. Rather, we'll stop point by point on several components which are crucial to the multi-particle extension of the single particle localization theory. And at any point, please don't hesitate to ask me, where are we exactly, what are we doing now, what are we going to do? Okay? It will also serve beside this real audience. There is also a virtual audience. It is recorded and probably transmitted live. So your questions will be useful for the virtual audience. Okay, so this is, well, I would say basic reading for this topic. And it's not time yet to discuss the content and relevance of each contribution to this new area. I think it will be more appropriate to do in the second half in a week. Okay? But let's say that the importance of this new area of spectral theory of disordered quantum systems has been quickly recognized by international mathematical community, and Simona Warzel in joint talk with Michael Eismann gave a talk at the 16th Congress in Prague.
Sorry, what is MPG?
Mathematical Physics, Analysis and Geometry.
And JSP?
Journal of Statistical Physics. Okay. Well, actually, since, as I have already said, I'm going to speak about one particular approach to the localization in general and to its multi-particle extension, or let's say extension to the quantum systems with interaction. I I cannot escape one task, which is important and still, well, rather difficult. I cannot not explain you what is a multi-scale analysis in its single particle variant. However, if one does it properly, point by point, in full detail, it will be worse than never-ending story. It will be never-starting story, because that will take 150% of my time. So, on the other hand, I cannot just make a hand waving. A compromise that I propose will be that I will give within this mini course a crash course of multi-scale analysis, and then we will see how the components of this method, MSA, can be extended in which limits to the particle systems with interaction. Okay, so for a few minutes we are going to we are going to discuss the single particle systems, and the bold-face notation will be usually reserved for the multi-particle system. So just this script X and Y and usual not bold-face G refer to the single particle system. Of the same time as described before, so let's say we are on the lattice, or a nice graph with a polynomial growth of balls. It is just as good as a periodic lattice. IID are external random field with nice distribution, say with bounded density, completely supported bounded density, or Lipschitz continuous, or Hodder continuous, and we are going to ask what can happen in a system with a subject to a random field. Well, it all started more than 50 years ago, and today we know several different manifestations of the Anderson localization phenomenon. Well, for example, one has in this context, usually one has fast, most often exponential decay of the kernel of the resolvent, called usually green functions, away from the diagonal. That is, for x, far away from y. And speaking of mathematical history in multi-dimensional setting, I'm not speaking about the works made by one of the people present here in one dimension, but speaking of multi-dimensional context. The first mathematical result was about the fast exponential decay of the green functions in the IID random potential. That was a work, well-known work by Frederick and Spencer. Okay, so it happens that just the exponential decay of green functions is not yet the fully developed localization in all its manifestations we know today. Well, the closest thing to it is the positivity of Lyapunov exponent, which it is exactly in one dimension. Okay? Well, in several dimensions, let's say in 2 dimensions, there are too many directions, and there is no well-defined notion of Lyapunov exponent. Still, it is often considered this is a close analog of the positivity of Lyapunov exponent situation, where the g of xy goes exponentially to infinity as x minus y in distance goes to infinity. So g goes to 0. Thank you. Okay. Now, the most important, well, more important mathematically, at least, manifestation of Anderson localization, which came in the second paper by Frederick, Spencer, Martinelli, and Scoppola, is spectral localization, which may occur just in some interval, which is quite normal for discrete systems, or just in some interval, for example, under weak disorder, only in specific energy zones where the Lifshitz tail phenomenon occurs, one can prove by existing methods, prove Anderson localization. Okay, so pure point spectrum in some interval, and well, I should have written fast, usually exponential decay of the respective eigenfunctions with eigenvalues in E. Well, bona fide eigenvalues in L2 square sample with eigenvalues in I. What happens for eigenfunctions, or generalized eigenfunctions outside the interval I? Well, it depends. Okay, now probably the most impressive, yes.
What is known about uniformity in direction of the decay of the eigenfunctions?
The way it is proven, it is, so to speak, isotropic.
Isotropic.
But what is proven? You prove some upper bound. The upper bound, the way it is proven, is isotropic. For the rest, I'm not qualified to answer the question. Now, probably the most impressive.
Doesn't allow to introduce the Lyapunov exponent.
Not really, no.
Not really.
Not quite. No. Okay, so another manifestation, I won't say for the third time it's most impressive, is the dynamical manifestation of the localization, meaning that if you act by the propagator generated by the Hamiltonian, random Hamiltonian H, then in the case where localization occurs in the entire R, over, let's say, over the entire spectrum, then you just act by the entire propagator on some complex Laplace function, and the result decays rapidly, for example, exponentially fast, if you manage to prove that. Well, to measure this decay, you can act on the result of time propagation by ITH on X, chi X, by an operator or multiplication of a rapidly growing function A, which, well, depends on what you can prove. If you can prove that the norm, well, this is actually an operator, and this is the operator norm. This operator of multiplication by local function, then unitary operator of propagation, and this another operator of multiplication. It's the operator. If and this operator is random, you take the expectation, and if the expectation is finite for this rate of growth, well, you say that the rate of dynamical localization is 1 over function A of R. Okay. Yeah, maybe just to complete this short discussion. Today, in the single particle localization theory, we know that usually under normal circumstances, these are essentially equivalent manifestations, and physicists, as always, knew it long before mathematicians. By that I mean that if you have sufficiently constructed control on the green functions, then the rest you can do also. It is not automatic. We know in one-dimensional quadriperiodic systems that Lyapunov exponents may be positive, and still there is no pure point spectrum, right? We know it's not an automatic implication, but usually, unless the system is very, let's say, specific, determinate, very, very, very special, you have all of those implications. So that is why usually we start with the green functions. Now, among the technical ingredients, we are going to use, the most important is the so-called geometrical resolved inequality, which starts with a geometric resolvent identity. Well, let's just second resolvent identity for Schrödinger type operator. Well, in this form, to apply this, to obtain this GRI, you need the kinetic energy operator to be a finite difference second order operator. Well, then if you decompose some volume lambda into disjoint union of lambda prime and lambda double prime, which are touching, have a non-zero, well, non-empty boundary, common boundary. then you can decompose the Laplacian as a sum of Laplacians in each area plus the hopping terms across the boundary. And I denote this hopping operator by gamma. Then you obtain this by usual second resolved identity.
Lambda 1, what is lambda 1?
Lambda 1, it should be lambda prime.
Lambda
Well, lambda prime. Should be lambda
two
prime.
primes.
The second is lambda.
No, second is it is skew splitting of the green function. It's not the direct splitting like in fractional moment method. The green function in the entire volume lambda is split into a series of two-leg paths. First, from x, you have to go from x to y. You do it in two steps. First, you go from x to some point in the internal boundary of a subset lambda prime, which contains x. Then you make a hopping by the operator gamma, and you continue from the nearest neighbor, which is outside lambda prime. This is why, and you continue this journey with the original initial green function in the entire volume lambda.
So x is in lambda prime.
Yes, x is in lambda prime and y is outside in the complement. Okay, to make some cumbersome notations shorter, I suggest to use this notation. It's a bit ambiguous because this symbol curly wedge has to be labeled by the volume in which you assess this norm. But, well, I find it quite useful. It symbolizes the decay of green function from the center to the boundary. Okay, so usually one takes just the maximum of the green function in a small. Now we are taking as an example of lambda prime a ball, or let's say a cube, which is a ball in Mach norm on the lattice of some radius small l. Now, usually one takes just the maximum of the matrix elements of the h minus I between x, and which is the center, and y, which is on the boundary. Well, the estimate I'm going to make require, or let's say suggest, that you multiply this maximum by the cardinality of the boundary. Okay? Then we will see why it is convenient just in a moment. First, so we take this particular case, lambda 1, again, it should be lambda prime with these notations, is a smaller cube in a larger cube lambda. Okay? X is in the center of the small cube, and y in the exterior area. Now, by taking the absolute value of the sum,
you probably can draw a picture on the board, right?
Oh yeah, thank you.
Because
Yeah.
you have already introduced, I don't know, 3 or 4.
All right. Okay. So this is lambda, a larger block, larger cube of radius L of some center, it doesn't matter which one. Now you take a smaller cube of center X, which is a cube of radius small l. Now you take y outside this small ball, and the geometrical resolvent inequality gives you an upper bound of the green function between x and y as the sum of terms. Each of them is a first leg from x to u. Then the hopping term, which is basically unity for usual from difference Laplacian to the nearest number u prime. So this is 1. This is a small green function gl, and then you travel all the rest of the journey from u prime to u. Okay. Now we see that indeed this compact notation is quite handy, and the green function between x and y in the large volume is bound by this kind of a norm which estimates the decay of a green function in smaller cube from the center to the boundary. You take the worst case scenario and it gives you this curvature norm. Okay, and the rest is the maximum of the original green function in large volume taken between the exterior boundary of a smaller ball all the way to y. Okay, well, imagine that we have this norm at a small number, let's say much smaller than 1. The smaller it is, and the better it is going to be for localization. Then it remains a sort of subharmonicity, on the lattice, of course, except for the fact that this subharmonic inequality, I will probably call it more often dominated decay of the green function. This kind of subharmonic inequality holds only for a specific radius. You are not necessarily empowered to impose this inequality for any radius, but for some L, it has to be assumed, and this is a starting point of the induction in scales. Okay, so if we introduce a function fy, which is of course labeled by the destination point y, yeah? Then we have for this function this kind of, so to speak, subharmonic inequality. Now, what we are going to do? Well, assume the best case scenario. And again, let us return to this picture. But if we know that each jump of length exactly small l produces us a factor, which we hang on the remaining part of the green function of the original volume, then we can iterate this, so to speak, subharmonic inequality, and we end up with a high power of the quantity, which I didn't by q. Yeah. It helps to introduce a function which is radial, depends just on the radial variable. To forget about the multi-dimensional problem and have only, well, an iterated inequality system for a function on just integer interval and nothing else. Okay, so capital F sub y, like f, it should be labeled by y, it's a maximum.
It's probably y, no, x minus u. Y. Only one y and only one u in this formula.
Let me
What is
see.
wrong?
Okay, let me see. What should be f of x? Nothing is wrong. We have to assume that the large ball is centered at u. Okay.
And y, what is y?
Y is a fixed point here.
Where? On the ball?
On the border of the, well, let's say close to the border of the large cube. Okay. So we start with a particular problem. We have just one point x.
Yeah, but where is y on the right? Small f is?
Small f should be labeled by y, but it is not, I'm sorry. Okay, then we have this, well, yeah, so now we take the maximum, so everything is expressed in terms of the decay of this function, capital F sub y. Each time we increase its argument by L plus 1, well, L for the small cube, and plus 1 because of the Hopin term in the Hamiltonian, in the Laplacian. We get Virchow factor of Q. And of course, we have to divide the entire journey from X to Y. Let's say we start with X equal to the center U of the large ball. Then we have to divide the entire journey by the small steps. Take, of course, integer part of it, and we get what we need. If Q is e to the power minus ml, then we get the exponential decay with rate m in the entire ball. That's the way it goes. Now, there are different ways in the scaling scheme, and this is going to be inductive analysis with a growing system of scale. There are several ways to choose the sequence of scales. Historically, the first one was the sequence Lk plus 1 equals, well, integer part, of course, of Lk to some power, let's say 3/2, but any number bigger than 1, of course, otherwise there is no growth, and sometimes there is some limitation. More often, you take a power between 1 and 2. Okay. So this is one of the possible choices, but there is a different, this choice is very convenient to prove exponential decay of the kernel of the resolvent away from the diagonal, and ultimately decay of the eigenfunctions. But there is a different scale, one system of scales. Lk equal to L0 times y to the power k, where y is an integer bigger than 1. This choice of the system of scales does not allow you to prove directly exponential decay of green functions, let alone eigenfunctions. However, it is much more handy for the proof of sub-exponential, fractional exponential decay of first of the green functions and then eigenfunction correlators, that is strong dynamical localization with sub-exponential rate, and also sub-exponential decay, fractional exponential decay of the green functions. So let's stick to this scale, and let's see why it is indeed handy to prove quickly, rapidly, easily sub-exponential decay of everything. The point is that the original works by Furrick, Spencer, Martinez, Scoppola didn't allow to prove strong dynamical localization with super polynomial rate, let alone sub-exponential, because in the expectation, well, the expected quantity has to be small with very high probability. If it is even exponentially small, but with probability which is 1 minus something which is polynomially small, you cannot have expectation as small as you need. This scheme, on the other hand, allows you to do so. So you make a concession, you trade the rate of decay which you prove for green functions and for the eigenfunctions. Instead of exponential, you get just sub-exponential. But you also get sub-exponential decay of the probabilities, of unwanted probabilities. That's why it is useful. Okay, now let's see why it gives you more than one could imagine. If, let me see. This small factor Q was due to the decay of green functions in the small cube of size small l. Now let's say that small l is Lk. It is Lk, okay? And the decay that we have proved at the previous step, starting from the first step of the scale induction, is Lk to the power minus bk. Well, written that way, it looks like polynomial decay. But let's see what happens with the exponent of this power law bound. Yeah.
What is the This notation? Sorry.
Oh, I'm sorry. I had to say that it's a maximum value of the function, which is the first argument, over the set, which is the second argument. Sorry about that. Now, imagine that in our journey from the center to the boundary of a larger ball of size Lk plus 1, we make at least two good steps, where we get the decay provided by Q equal to Lk to power minus bk. Then this function m, which measures the overall decay, would be given by Lk to the power minus b times the number of good steps, at least 2. Well, this is the good part, negative exponent, that's what we need. Unfortunately, there are some others, and quickly it comes from the fact that, let me show again. You see, each time we show some small factor, let's say we hope is small, and the rest is the maximum of the green function. But even after making the maximum number of steps, we still have on our hands the maximum of the green function of the larger ball, which we are going to assess over the entire ball. So to break this vicious circle, we have to have some a priori bound on the green functions. And that's why, that's why there is something which makes our life not as easy as we'd like it. Still, I will explain it a bit later, but indeed what is not neglected here can be more or less neglected. Then we get the initial bound raised to the power 2, which gives us, well, y to the power minus 1, Lk plus 1 to the power minus 2 bk, plus something. Okay, even if we take rigorously account of what is missing here, we get something, for example, like minus 3/2 bk. And each time we are going to raise the exponent of L to the power 3/2, which means that we get this. Well, this L dots around K mean replace something cumbersome like green function in the ball. Usually it produces your 5 to 7 story notation. But the K at the scale L is about that. Lk to the power some constant times 3/2 to the power k, double exponent. Okay, now let's see why the choice of multiplicatively growing scales produces fast decay here. Because 3/2 of any number bigger than 1 to the power k is comparable to y to the power k, and y to the power k up to a factor of L0 is Lk. So this is some maybe fractional but power of the scale Lk, which means that the decay which we obtain in the green functions after k steps of scale induction is fractional exponential. It's no longer a polynomial. It's much faster. It's not exponential, not truly exponential, but fractional exponential. That is the big advantage of this multiplicative scaling scheme. Now, like I said, or rather I have neglected the bad cubes. It was, quite optimistic to say that all cubes that we were encountering in our journey from the center to the boundary of large blocks were good. Maybe not all of them are. And since everything is random, it may happen, everything nasty can happen with some probability. With what probability? That's the question. Well, first of all, there is no shade gray here. Okay, doesn't matter. So what I'm going to explain now is that if in this journey from the center of the ball of size Lk plus 1, only one ball can be bad, encounter in our journey from the center to the boundary. That it's not going to destroy this beautiful picture which I explained you up to now. Well, let's say this is our point X, this is a point Y, everything is in a large box, and in our journey from X and Y, if we just look first, what are the possible bad cubes? Bad meaning that the decay at this scale Lk is not the one which we counted on. Yeah? Then, well, it should be great actually. This okay. Let's say we encounter one cube and assume in addition that someone tells us, or we can estimate by probability, that no ball or cube disjoint with this one can be bad. Why this is a reasonable assumption? Because if two disjoint cubes have some random events which are not desired, and if we have independence, which we do have for the moment, then the probability of a double occurrence of these events is a product. That is, you have to square some probability of a nasty event to and give an obtained larger power, and therefore there's a hope to rule out this by probability, and that's the way it goes. As to the application of geometrical inequality, now we can stumble on this ball. What we do? Well, let us recall that ourselves that the green function is a function of two arguments. So first we can say that, well, we fix some a point y or some other point in this ball which doesn't touch the bad one, and make the random the radial descent is from this smaller ball of a radius r prime, which is the maximal radius, which doesn't lead to the intersection with a bad cube. We make a descent and shop q to the power r prime. Now we fix the first argument and do the same procedure with the second one. Well, there is some subtle thing which I'm not going to discuss. To make this work smoothly, you have to impose not just any, but periodic boundary conditions, or change a little bit, regulate a little bit the scaling scheme. Okay, there is a way to say that the decay that we can guarantee in presence of a single bad cube, provided that no one else, well, no a cube disjoint with this can be bad. Just this one. Its decay provided by q to the power r prime plus r double prime, which is essentially x minus y in distance minus the radius of this ball. So we lose something, but not much. Okay. Now about the probabilities. Like I said, well, something unwanted can happen in a small ball of radius Lk in our journey of size Lk plus 1. Assume that the probability to have a bad ball is pk at the scale Lk. The probability to have two of them, that is, not to have this picture, not just one, but two cubes would be bad. It's a square of pk. Of course, we can have to take into account the entropy. We have to, the combinatorial factor coming from the number of all pairs. Well, basically, this capital C is what? A dimension of the lattice times 2. Yeah, that's it. That's it. If pk is much smaller than inverse of that, well, we almost don't feel the presence of this polynomial factor. Now, another component in this probability which we have to take account of is the probability not to have a priori bound in the large box, so that it doesn't destroy q to the power L. So this is a probability that the entire box has the energy and we using this geometrically resolved inequality for the green functions at a specific energy. It's a fixed energy analysis. So if the green function is big, it means that the resolving operator has a large norm. It's after all a self-adjoint operator. So its norm is bounded by the distance, well, actually equals to the inverse distance from E to the spectrum of the operator. Now we see, we will see it in a moment. If we look at this iterative inequality, we will see that as long as pk is not as small or compared to wk plus 1, if it is a leading term, then basically wk plus 1 is more or less negligent. It's less than half of pk. And therefore, the step from pk, p sub k to p sub k plus 1 is raising pk to the power 2. Well, let's take account of this factor. Let's take to the power 3/2 again. Okay, a generous 3/2, we get it. Which means that as long as pk is leading term, it is not smaller than or compared to wk plus 1, pk grows again super exponentially. Some number to another number greater than 1 to the power k. And again, by the same calculation we just made, pk would be a fractional exponent with some kappa. It's almost the same as k, but it's a kappa actually. Okay, now how about this note? Well, now we have to estimate the proximity we can allow of the spectrum to a given energy. And this is about the eigenvalue concentration estimates. Okay, today many kinds of Wagner type estimates are known, starting from the Wagner estimate proved in 81. But what I'm going to present you actually would seem as a joke to any person who made any contribution to the eigenvalue estimation theory, because we will see that it's a very inefficient way. But unfortunately, it so happens, it's one of the surprises of the localization theory of interacting systems, that it is questioning your beliefs and contesting everything you were taking as granted, taking for granted. And so happens that the eigenvalue concentration or comparison estimates required for the interacting systems are often much nastier than in the single particle setting. And to make, to prove the most efficient decay estimate for the eigenfunctions or for eigenfunction correlators, for 3 particles or more, 2 particles is a specific case, and I will explain why. For 3 or more particles, the only way to prove what is needed for physically relevant decay is to use this, again, a joke of a Wagner estimate.
It's enough.
Still,
But it's enough localization.
yes, it is, it is enough, but not in all cases. But particularly, it is very, so far it is very restrictive in the continuum system, but that's in the 1 week. Okay, but on the bright side, this is a proof in 3 or 4 lines. Okay, it requires some basic knowledge of some basic statistics. I wouldn't even say probability, but statistics. If we have a finite sample of random variables, and our sample will be a sample of values of the potential, with points with sites x, in some finite volume, finite subset of lattice lambda. Okay? Then we can always introduce the sample average, or empiric average, or whatever word you like to use, and the rest is declared to be a fluctuation, a lot of fluctuation. You have a plateau, which is a random but constant on the sample plus the fluctuations. So far, nothing serious done. But still, then the potential is decomposed as operator in the scalar operator, the unity operator times the sample mean plus the fluctuation potential. And it so happens, as we teach it in the elementary courses of probability and statistics, that if the sample is Gaussian, then the sigma algebra generated by the fluctuations and the sample mean are independent. Meaning that we can condition, if we like to, and we are going to like it, condition on the fluctuations eta, meaning that we are going to condition on the fluctuation of potential V, and all which remains alive in our potential, in our operator of multiplication by the random potential energy, is this scalar operator, a random constant. Okay, if the operator is decomposed, well, if V is decomposed, well, put in H tilde the kinetic part and the fluctuation potential, then the entire operator is a random constant, multiplication by random constant, plus the rest, which we condition on. Therefore, every eigenvalue is the sample mean plus something which is measurable with respect to fluctuations. That is non-random under conditioning. Period. We get the regularity distribution for each eigenvalue, therefore the entire spectrum, of the same kind as the sample average. There is, of course, a catch. I said, let's take a Gaussian sample. It seems to be an innocent problem, and I was ashamed writing for the first time in a preprint an estimate for uniform distribution, which is, very simple calculation. We are going to make it. And since then, for a couple of years at least, I have been asking people, analysts and probability statisticians, what about more general distributions? It seems to be, well, more or less unexplored area, or everybody, including myself, in this community in which I discuss it, didn't know about it. So as of today, one can prove, one can use a similar trick for the Gaussian, exactly Gaussian distribution, because of this exact independence. Then by simple calculation, losing some power of the volume, making the bound inefficient, in that way not non-optimal, you can prove it for the uniformly distributed IID sample. You can then perturb the uniform distribution by a smooth density. And I'm sorry, again, say smooth density. Not smooth probability distribution function, but one has to, I have to require the derivability of the probability density. I think one can go a little bit to let's say, further continuity of the probability density, but still, it seems to be by far too much to ask for. So there is a class of probability densities, and only probability densities, for which you can play this trick. I still don't know if this is true for the Hurdle continuous and therefore possibly singular distribution of a single side potential. I just don't know, and I'm ashamed of that. Okay, so because even in the Gaussian case, because of the maximum of the density, which is bound, of course, but it is proportional to 1 over lambda, you have a wrong power of volume in the final eigenvalue concentration estimate. It is not 1. And this way, again, this is a weakness of this approach. You cannot even prove the existence of the limited density of states. I'm sorry, but that's the way it is. Okay. But like Misha said, it's something, better something, but nothing. Okay, it is clear why we get a non-optimal decay, because of all degrees of freedom, and we have model of a cardinality of lambda of them. We take just one component, the sample mean, and we throw it away, and this is absolute inefficient way to do it, and that's why we get a wrong power. Okay, I think that's enough for this, and maybe this is a good point to make a break.
Okay, thank you. So,
Okay, so the bottom line of this discussion, this, so to speak, crash course of multiscale analysis, in the version, by the way, this version was originated in, first it was a PhD work by Enrique von Dreyfus and the advisorship by Tom Spencer. Tom in 87. In 88, Tom Spencer published a short paper, but rarely cited, but very useful. I think very bright paper in the Journal of Statistical Physics, published in 88. It was about the boxed variant of the multi-scale analysis, which was originally made by this Nobel company in the Italian lattice. And in 89, Henrique von Dreyfus, who moved to California with Abel Klein, wrote their famous paper in Communication Mathematical Physics in 89 about the variable energy or energy interval variant of the multi-scale analysis. But after that, the first bold step toward using the multiplicatively growing scaling sequence was made by Germain and Klein in 2001 in their paper about bootstrap multiscale analysis. And this is, well, let's say, not exactly the bootstrap I'm explaining you, but it is inspired by the bootstrap and uses components thereof. Okay, so this multiplicative growth of the scales results in the decay of the green function. Again, this curly edge means how decays the green function from the center to the boundary of the ball of size Lk. It's bounded by a fractional exponent of Lk, with probability which is at least 1 minus again, it's, I didn't use the hat, it should be raised to the power minus Lk to the power cap. So both quantities, the decay and the probability not to have that much decay, are sub-exponentially small. And therefore, if we are fully prepared to take the expectation and get the expectation that small. I mean, as small as the maximum of the two, but both are fractional exponent, and we get a fractional decay. Okay, what we are going to do from here? Well, like I said, positivity, fast decay of the green functions, and so far it was only decay of the green functions, is the analog of the positive Lyapunov exponents, and therefore it's the first step toward localization, but not yet the localization, not even the spectral localization. So to prove pure point existence of pure point spectrum, or the fact that there is only a pure point spectrum for discrete models under large disorder, for example, one have to infer from the fixed energy analysis energy interval analysis, and prove that not only just a single cube cannot be bad with high probability, but if you take a couple of them, one of them at whatever energy, and you see there's a continuum of energies, which is very bad for probability. Even for two cubes at any energy, one of them, at least one of them, has to be good. This is a result of energy interval analysis, and today there are soft ways to infer it from the fixed energy analysis, using, of course, using non-degeneracy and regularity of a single site potential. It is not automatic in the full generality, but here it takes place. Okay, one of the soft derivations actually goes back to a paper by Martinelli and Scopola, published in '85, if I'm not mistaken, who used forbidden theory and Chebyshev time inequality, but not just in the disorder space, but in the augmented energy disorder space. And that allowed them to show that like positivity of Lyapunov exponents in one-dimensional case, fast decay of the green functions rules out absolutely continuous spectrum. Okay? This kind of argument, Chebyshev argument in the energy disorder space, led Ergodic and Vesserich to an improved version, namely the derivation of the energy interval estimates from the results of the fixed energy analysis. Okay. And for the derivation of the strong dynamical localization, that is decay of the expectation of the eigenfunction correlators, there is even a softer and shorter, easier proof. Again, due to Germany and Klein, again, the paper from 2001 on bootstrap analysis. This was not the only proof of derivation, of implication. Fixed energy analysis implies strong dynamical localization. It started from the paper by Germaine de Pièvre in 98. And then in 2001, two papers appeared by Damanik and Stallman, who proved that using the notion of the localization center as some tedious analysis of their geometry, and Germaine and Klein, in a very general situation, proved in a soft way. And this soft way becomes, well, an elementary application of Bessel's inequality, and I say these words are responsible, nothing else. Just a simple application of Bessel inequality proves you that from the energy interval analysis, you can derive strong dynamical localization. Okay. And we will see at least a sketch of this proof later in the talk. Okay, now how about the rate of decay? Well, today it is known, if you didn't know before, just please be aware that today the only way to prove exponential decay of the eigenfunction correlators is to use a fractional moment method, originated as an Eisenman-Molchanov method. And it's a big improvement as compared to the fractional or polynomial or fractional exponential decay given by multiscale analysis. But again, in this paper by Germaine and Klein in 2001, they have proven that using the multiscale analysis as a sequence of several, or four actually, interconnected analyses, you can start with a very weak hypothesis. For example, you start with a hypothesis that in a cube of size L0, you have with polynomial probability, polynomial decay of green functions. You can end up with exponential decay of eigenfunctions, not of the kind eigenfunction correlators, but eigenfunctions with sub-exponential probabilities. Okay. Now, I recently realized, trying to understand by how far you can push this bootstrap, B for bootstrap multiscale analysis. I realized I can actually put all the phases of the BNSA in a single algorithm, in a single scaling algorithm. And this single algorithm, like Renon group in many physical problems, gives you the decay of the eigenfunction correlator at the distance L, such that as L goes to infinity, then the double log of epsilon divided by log of L is 1. And actually, you can even prove that if a scale is Lk, and again, it's multiplicative, scale, which is by some internal trigger is transformed from the multiplicative to super exponential scale. You can prove that the exponent, you have e to the power minus L to the power minus kappa. But this kappa decays exponentially with k. So I would say that for all intents and purposes, the properly reformulated bootstrap multiscale analysis gives you, essentially what the physical scaling theorem gives you. Asymptotically exponential decay of the eigenfunction correlators. Okay.
Where's the double rule? Can you explain it?
Sorry, what is your question?
I'm not sure I understand. So, shouldn't gamma decay exponentially in L?
That depends on the method. It's not the decay of eigenfunctions. It's decay of the eigenfunction correlator.
But shouldn't it be exponential or no?
If you use a fractional moment method, yes. But if you start and go on with multiscale, you cannot prove it exponential because you can always you're always using the Wagner estimate, and the Wagner estimate has to be sub-exponential. Otherwise, you lose all the mass.
Okay, so basically this establishes exponential decay of gamma. with
But
zero
only in the
constant.
limit. Only in the limit. Only in the limit.
What's it? 1 minus kappa k is less than this?
Yeah. Well, you raise lk to the power kappa k. The closer kappa k is to 1, the better it is. And it can be exponentially close to 1. I mean, exponential not in lk, but in k. But if you do it in incremental steps, with this uniform algorithm, just one algorithm, it takes from the beginning and gives you all the way to the limit. And then with the number, with respect to the ordinal number of the step, it decays exponentially.
Do you know the constant C in that estimate?
Well, you can see it here. You can see all the detailed estimate. It is quite constructive. It is not sharp. What is written here is by far not sharp. Okay. Further. Okay, so now the crash course is more or less finished, and we have to push these techniques to the interacting random systems. Okay. So, yeah, by the way, let me stress it again, that this discussion, however short it is, it can be, shows that we can indeed focus almost all the time on the decay of green functions and only be in the context of the fixed energy analysis. Of course, it has to be it has yet to be shown, and I will show it, that one can indeed, even in an interacting system, derive at the very end, when you prove some decay of green functions of the interacting system, derive from this decay of eigenfunctions and of their correlators. And my point is that these two derivations of dynamical and spectral localization are almost as soft as in one particle case. But it depends on what kind of eigenvalue concentration estimate you have. It's like having a powerful engine and fuel. How fast you go depends on your engine. How far will you go? Well, it starts from the fueling your car. So the fuel here is the eigenvalue concentration analysis. Yeah, and as we start thinking about multi-particle system and decay of anything at all, it turns out it's not an innocent question. How do we measure the distance? Now, not in the physical space, but in the multi-particle configuration space. Even, well, it happens that in a two-particle case, and we'll see it in a few minutes, there is some specific geometrical, well, miracle. But starting from 3 particles and on, one can measure the distance in at least two different, well, actually three different ways, and they are not equivalent. Okay. Well, first idea would be to take, well, what is the configuration space of n particle system? And by the way, I'm sorry, Bernard, not to have answered your question before. I am not considering any kind of quantum statistics. One could be considering them, but it's a system of indistinguishable particles, which means that if you prove something for the full Hamiltonian, you prove automatically also for the symmetric and antisymmetric sectors. But actually, it turns out you can prove everywhere. Okay? It's not physical, but you can do it. Now, so if the configuration space of n indistinguishable particle is, of course, a Cartesian product of the physical space in n replicas, then one natural idea is to take just a max norm or two norm or one norm in the product space. That's it. Well, it seems to be natural from the purely mathematical point of view, but first, it's not natural for the physicist who is usually taking some quantum statistics, whether it be a Bose or a Fermi, right? And there is one more obstacle for using this norm. If we take the interaction symmetric, and the way I have written it, it was symmetric. Okay? So assume it is symmetric. The random potential, which is just sum of V of xj, is also permutation symmetric. Kinetic energy is the sum of kinetic energies. It's permutation symmetric. Therefore, if you take a multi-cube in this n-particle space, and another one obtained by permutation, by some permutation, any permutation of the coordinates, then you have a unitary equivalent operator. Two unitary equivalent operators have the same spectrum. What kind of small denominators you can shop, non-zero small denominators you can shop for this pair? Nothing. So therefore, the norm, just the norm distance, is not good for proving any kind of decay of any kind of physical or mathematical quantity relative to a multi-particle system. Okay. Good. Let's symmetrize the, let's say, max norm distance. I will often use short notation S norm with S in red to remind that it's a symmetrized norm distance. Well, is it good? Well, of course, it's natural distance if you take, for example, two particles living in one-dimensional lattice. Then the configuration space, well, let's say, the functions on the lattice Z2, if you take symmetrization or anti-symmetrization, can be represented as the space of the functions on just half of the space, above or below the main diagram, right? Okay, that's a part of it. And the max norm distance in this half of the lattice, in the Bose or Fermi sector, would give you a natural distance for a physicist. Is it good? But not quite for the kind of eigenvalue concentration estimates we're going to need. Why? Well, this is a problem. The first and by far not the most nasty problem we're going to encounter here. Let's take in two particle space, two configurations. Let's say that each particle lives in Z1, so the positions are just integer numbers. First configuration is 0, 0, and second 0, R, meaning that the first configuration this is our physical space. This is 0, this is how are they called? R or L? R. R. So there are two configurations in the same place making the configuration A, and another one. This is the configuration B. Okay. So one of them is extremely clustered, the other is disjoint. Now, what before speaking of eigenvalue comparison for this for the Hamiltonians in some cubes, let's take cubes of size 0. I mean that the cubes reduced to a single point in this product space. One cube is just the set containing the site A, both face A, and the other cube of size 0 is centered at B. Now, there is no kinetic energy, there is no interaction energy. Well, if there is any interaction, forget about it. Let's just take the potential. What can we say about the, so to speak, eigenvalues for these reduced Hamiltonians? Well, just the values of the potential. For the first Hamiltonian around A, it is 2 times V at 0. For the other one, it's V of 0 plus V of R. Let's take R of as many light years as you wish. Does it matter? No, because these two random variables, which are denoted Z1 and Z2, these two random variables, forget about any spectral theory, are interconnected, correlated, related at any distance in the same way. I don't say that correlation coefficient is close to 1. No, we know that the nastiest problems come where, from the situation where we don't have small or large parameters. Their degree of correlation may be of 1, but they are correlated exactly in the same way at any distance, period. So, and this is about just single-side cubes. How about cubes of size 1,000 by 1,000? Seems to be very bad. Well, it's not as bad because there is such a thing as conditioning. If we condition both the variables on something which freezes a good part of it, V of 0, conditional V of 0, then what remains from Z1 is just a constant. Under conditioning, it's a constant. And the second is, again, another constant, plus a random variable which remains alive. So the distance between them, well, actually it should be minus V of R, I'm sorry about that. Still, the distance between these two variables, random variables is a random variable which we can control if we know the regularity of distribution of a single site potential, plus a constant which is absolutely irrelevant. So any estimate for the small denominator between these two silly eigenvalues can be done by taking expectation of the conditional probability. And you are done. But what we used here, a part of using this condition trick, we used that these two subsets of Z with two particles at 0 for one configuration and 0 and R for another, these two configurations as sets are distant in what's called Hausdorff distance between the subsets of symmetric space. Let me recall the usual definition. If you have some metric space, and I'm sorry for using again M, but in different way now. It's some abstract metric space with some distance on it. Hausdorff distance between two subsets is the maximum of the two quantities. The first measures how far at least one member of the X community can escape from Y, from the entire Y. And this is the symmetric component. So you take the maximum of the two. And if two subsets are Hausdorff distant, then at least one of them has its member escaping from the other. And that's exactly what we have used. And let me now stop for a few seconds and say that today, well, I don't know how to measure here the percentage, let's say 80 to 95% of results about Anderson localization in a random interacting system is about the decay of some quantities like eigenfunctions or their correlators with respect to Hausdorff distance. But I also promised to say what's specific about two particles. In the two-particle space, I mean in the square, in the Cartesian square of a given metric space. Yeah, metric space. The Hausdorff distance and the max norm, max distance are equivalent. It's a simple geometrical exercise. But it is no longer true for three or more particles. For the Cartesian cube or more, these two distances are very different. And I'm sure there is some discussion later on the slides, but let me just continue this and show what happens when we have at least three particles. Why all this is, well, the equivalence is ruined. Because you can take now the following two configurations. Again, let's say this is 0, this is R, and the first configuration consists of a cloud at or around the 0 point and some point very far away. Another one, the second one, is the opposite. Well, we have to have three particles. Well, if you take only one particle for the second configuration here and two over there, let's see what happens. What is the Hausdorff distance between these two subsets? 0. It doesn't matter what is the Euclidean distance between the points 0 and R. It doesn't matter. And if you take any cubes around this, I mean, three-particle cubes, around the yellow configuration and around the blue one, you will always have maybe enormous astronomical distance in a sense of norm or sim-norm distance. But the Hausdorff distance will never distinguish that. Meaning that we can run into severe problems with estimates in Hausdorff distance. And let me also tell you this. What is the final result if we forget about proofs and mathematics? What will be the final result? How could one formulate the result of this phenomenon? Well, let's say you have a wire. And what we can prove with Hausdorff type estimates is that somewhere in the middle of the wire, it's an absolute isolator. But one cannot rule out the possibility that from one extremity of the wire, the current passes to the other one. It wouldn't qualify as an isolator, it would qualify as a conductor if you have this phenomenon between the extremities. It doesn't matter how good isolator it is inside. So this is the kind of physical implications we would get by working only with Hausdorff distance. Okay. Well, still in the framework of Hausdorff distance estimates, one can prove the localization of eigenfunctions and fast decay of eigenfunction operators, but only in an actually infinite configuration space. This example with a wire, it is still there regardless of the size of the wire. Any finite size would make you run in this problem. And let's say, speaking of cosmology, if someone discovered that our universe is finite, then the proofs accumulated since 2008, 2009, except for a few recent papers, would prove nothing about complete localization. It doesn't work in a finite universe. It's a bit of a joke, but there is also, well, some serious impact of this Hausdorff gluing together of configurations which physically should be considered as remote. Okay, but this is the list of results one can establish with the estimates in Hausdorff distance. Because somehow technically it is convenient. That's why it was used in 2009 in our paper with Yuri and in the paper by Heisman and Warzen. It is very convenient. It doesn't solve all the problem. That's the trick. Okay, now how about fixed energy analysis of multi-particle systems? In the fixed energy analysis, it turns out that all these nasty problems disappear, or let's say they don't appear yet. They appear only in the attempt to infer localization of eigenfunctions or of their correlators from the fixed energy analysis, that is, fixed energy analysis of green functions. And let's speak about the case of green functions. So we have our operator, H, and it contains the kinetic part, that is Laplacian, plus the interaction. The rest is the potential. And by the way, what is B is okay. Now we take our cube B as a product of faces, which are single particle cubes, which may be multidimensional, but each contains one particle. It's a Cartesian product, and we take the potential in this cube. Then this potential can be written in terms of, well, isolated, I mean independent values of the potential, multiplied by what is called occupation numbers. How many particles in the configuration X, which is X1, X2, Xn, sit at Y. That is the function ny sub y of x, which can be considered as a multiplication operator. And if you multiply this non-random particle number operator by the values of v, you assemble your full potential, full random potential. Okay, now the very fact that the projection of a cube on any face covers any point, all points in the projection, means that if we raise the potential on any face, that is, we have particle here, here, there, they may overlap or not, but if we raise let's say by a plateau, the random potential around any face, we add some constant to the whole, to the entire potential energy. And this is a direct analog of what's called complete covering in the single particle system, where there is a monotone dependence of the random potential upon each of the single side potential. Meaning that if you add some constant epsilon to every side, then you get epsilon added to n times n added to your entire potential. So this is a complete analog, and it shows that the methods accumulated in the single particle localization theory can work, and indeed any, let me see if I have this, no. Okay. So basically any method that works for single particle works in this situation also. And for example, that silly Wagner type estimate which I explained you, with decomposition in the sample mean and the fluctuation field, also works. So to prove Wagner type estimate in a single cube, not in a pair of cubes, here we got a problem because we got two configurations and two cubes around there. But if we have just one cube, there is no problem. It all goes smoothly and gives you enough to make run the fixed energy analysis and to prove fast decay of the green functions in any multiparticle system. This Hausdorff or sim norm distance doesn't just appear. Distance between what and what? We have just one center of the cube. There is no distance. Okay. Now, there is actually a small bonus coming from the part of ideal random potentials with analytic distribution, probability distribution. I mean, analytic probability density. It is well known since a work by Carmona, who used Molchanov's path integral formula, which is rigorous on any countable, locally silent countable graph, that one can prove under strong disorder assumption, prove analyticity of the eigenvalue distribution. Or let's say, if you're interested in the limiting density of states, you get analyticity of that limited density measure of states. If you are interested in just a single finite cube, you get that for eigenvalue distribution in that finite cube. Well, I don't know if you have enough time, but the idea of Carmona's method is the following. First, to prove that measure of states or eigenvalue distribution in finite cube is analytic, it is enough to take a spectral measure related to, for example, delta function at 0. Doesn't matter where. By ergodicity, doesn't matter. You take the Fourier transform. If the Fourier transform of that spectral measure, which is random, because you have a random potential, decays exponentially fast, then the probability measure has density which is analytic in a strip, period. So how can one assess this Fourier transform of the spectral measure? Well, you apply the Molchanov formula, which is exactly the following. What is what? There is a nasty, very, very nasty exponential factor here, and I put in red plus sign. We need decay, and we have plus 2 dt. D is dimension, it's not a differential. Now, RW means expectation with respect to a random walks. What kind of random walks? It's called often discrete Brownian motion with exponential sitting times and equidistributed jumps from a site to any of its 2D neighbors on the lattice. Okay, so what you get here is I square root of -1 raised to the number of jumps of that discrete Brownian motion times the, so to speak, finite cuts factor. Exponential of the I times the integral of V along the trajectory. Well, of course, here this is a jump trajectory. And you take f of at x, the process is x, at the final moment t, and you get the result of application of the propagator by time t to the given function. Yeah, I'm sorry. You have to take here expectation conditional on x, large X at 0, x equals small x. Okay? You start the jump trajectory from small x. You can write it as a exponential of I times all the values of the potential across all the lattice times the local times, the times spent by the trajectory from 0 to t on the site y. That's Molchanov form. Proof, you can prove it with tools used in any standard course of Markov chains with continuous time.
Sorry, is there a continuous analog of this formula?
If wishes were horses.
Okay.
Yeah. Okay. The rest is just a calculation. Somewhere you have to remind yourself how to compute the generating function of the Poisson random variable. Well, it's a nice calculation. It ends up in the competition between minus aj modulus of j times modulus of t, and j is the disorder amplitude, with some c coming from this growing exponent 2 dt and from the generating function. There's a competition. But you can win this competition with large disorder amplitude. And again, what about small g? Nobody knows. Okay. Now, so this will complete the proof. In one particle case, this very nice, very soft argument extends very smoothly to 2 or more particles, because the integral of the v of the total potential energy along the trajectory is the sum. I'm sorry, it should be some local times for the one process and another times vy. What is t superscript 1 and 2? You can actually represent your Brownian motion for 2 particles like a direct product. So at each moment, the particles sitting at some site may jump vertically in the direction of the second particle space or horizontally. And you have respective local times. That's it. That is to say that for a particular class of random fields generating the common potential, you can prove not just regularity, not just Lipschitz continuity of the eigenvalue distribution, analyticity. Okay. Now, how about two-volume estimates? Well, like I said, the fact that the projection of the cube on any face covers the entire space, and therefore, by perturbing, by wriggling your potential at every side at just one face, moves your entire potential up. Using this kind of monotonicity argument shows that you can extend the vector type estimates to 2, 3, and particles model without any significant difficulty. But now, if we ask ourselves what we can do for 2 cubes, then we run now in this program, with this problem. And first, we have to agree how we measure the distance between them. And if we realize that the Hausdorff distance is the most convenient, well, we proceed with the Hausdorff distance and use the kind of argument which I explained to you, but only for Hausdorff distant cubes. Now, and I think that will be probably the last topic today. What we can do in sim norm distance. Now we have this kind of configurations in the cubes which are in sim norm distance very far away from each other, but from the Hausdorff distance point of view, they are at a distance 0, well, of order of 1 or just 0. It's quite possible.
What is the sim norm again?
You take the norm distance in the product, and you symmetrize it by taking the orbits. You take the factor by the symmetric group, permutation groups. That is.
So what would be the sim distance?
No. Not here. I would say, well, x1, x2, x3 is declared equivalent to x sigma 1, x sigma 2, x sigma 3, whatever be the permutation sigma. And in the factor space, you have some distance.
So
you call it sim norm.
Is R for this case?
Sorry?
For the case on board with 2 particles at 0, 1 and R, and the opposite for the other configuration. The distance will be R, right?
Sim norm, yes. Okay. Okay, what we can do with just sim norm but not Hausdorff distant cubes. Again, let's do this decomposition of the random potential in the finite sample, in the sample mean and the fluctuation field. Then, effectively, we introduce one single and most important for our estimates parameter, sample mean for the configuration A and configuration B. Okay, in this example, the potential on the cube of size L around A is 2 times psi q of omega, because there are 2 particles from A at some set q. Well, okay, let me start again. Assume that we have 2 sets in the single particle configuration space. In this example, we take a Q, which is a set around 0, and the rest, the complement of Q. We decompose V only inside inside Q, where there are more particles from the configuration A than from configuration B. That is 2 for the one and 1 for the other. Therefore, this is 2 times sample mean plus the fluctuation potential. For the second configuration, with set at B, we have 1 times psi q plus the rest. Of course, these 2 guys are correlated. Both depend on psi. But the sensitivity to psi is not the same. If you take the difference between this guy and this one, you take 2 minus 1 times psi plus the fluctuation. Filter out, condition on the fluctuation, and you still have a non-zero integer multiplied by psi q. And if psi q has a regular distribution, we are done. That's the way it works. So, like I said, it was basically a joke for single particle system. But here, we do not decouple. Let me stress it again. We then do not decouple these 2 potentials or entire Hamiltonians because it is impossible. Because every single value of the potential affecting one of the Hamiltonians automatically affects or may affect the other, and vice versa. There is no way to introduce stricto sensu stochastic decoupling. There is none. But we use just the difference in the sensitivity with respect to at least one variable, properly chosen, and it is sample mean. By the way, the same trick works not only for the Gaussian or, let's say, quasi-Gaussian lattice fields. It also works for the Gaussian potentials in the continuum space. Okay, so this is exactly the calculation which I explained. The eigenvalue lambda I for one of the Hamiltonians is 2 times psi plus something which filtered out by fluctuations. Mu j is 1 times psi q plus the fluctuation random variable. The difference is a non-zero coefficient bounded by below, by the way, because we have integers. Okay. If it is non-zero, it is at least 1 plus something which is filtered out by the condition. Okay, so I think I still have 5 minutes to explain why the decoupling, which I suppose to be possible for this particular pair of configuration, can be found always for any n, for any number of particles, and for any pair of sim-norm distant centers of the cubes. Okay. Well, okay, here is the argument. So we have 2 cubes of size L in the n-particle space at large distance from each other in sim-norm. Okay, so let's say at least 3 particles. And we, to be able to apply this trick, we have to find some set Q. Oh, I'm sorry. Now I'm writing in the wrong space. The particle configurations live here, but as subsets of the physical space, they live in, let's say, Z. And this is Z3. Generally speaking, it's Z to the power n. Now I'm looking for some locus where there would be more particles from the configuration A than from the configuration B. First, I take, no, Z, on the Z, there is not enough place to draw. Let me take Z2. Okay, now I first organize the configuration A into clusters. Into clusters defined by the balls of size L. So I first decompose the first configuration into clusters with radius L. If the particles belong to different clusters, then there is some distance which we can impose 2L, 3L, 1 million L, whatever we like. These clusters are far away from each other. Now, the next step, yeah, by the way, in each cluster of cardinality K, there are K particles from A. Now we start also counting the number of particles from the another configuration in each cluster. In some cluster, there may be 0 particle from Y. So in each cluster with K particles X, there may be from 0, there is some number Nx and Ny of particles coming from this configuration. Now let's see as the formula. Okay, so the gammas are the clusters, and we introduce the occupation numbers Ni of X, the cardinality of those J, for which, let me see, Yg, of course, Yg belongs to gamma A. Similarly, we define occupation number of the ith cluster defined by the configuration X, but we take the cardinality of the particles from Y. Okay, the total number of particles doesn't depend on the way we count them, is n. First way, one way to count them is to take the sum of all occupation numbers of all clusters of X. It is equal to n. However, the sum of the numbers of particles of Y present in all clusters for X may be even 0. Maybe neither of the clusters for X is occupied by any particles from Y. It may be even 0. And in any case, we have this inequality. Therefore, the sum of the differences Nyx minus Nyy is non-negative. Okay, assume that in any cluster, number A, we have exactly as many particles from X as from Y. Therefore, we can rearrange, just change the labeling of the functions, and thus show that the sim norm distance between these two configurations is basically the maximum diameter of the cluster. And we chose the clusters to be O of L. Therefore, one of the two things, either all the occupation numbers are identical, and then the sim norm distance is not as much as we expect, and we can take it 1 billion times L. Or there is at least one pair for which Ni of X is different from Ny of X. Okay? Let's say that it happens for the index I naught. But because of this inequality, not all the differences can be negative. Therefore, at least one of them is positive. And since these are integers, at least one ni is bigger than y of y. Therefore, this trick with isolating subset of the single particle occupation, configuration space, where there are more particles from X than from Y, is always possible if we take the sim norm distance between the configurations. Well, more or less sharp estimate gives you 4 times L times N times L. Okay? So the sim norm distance by 4 and L guarantees that this trick with a sample mean and fluctuation works for any n. And I think that's a good point to stop here.
Thank you. Other questions? May I just quickly ask, so this Feynman-Katz analog, formula analog, which you call Molchanov, so it was for discrete Schrödinger evolution, right?
Right.
Is there something like this for discrete wave evolution?
Well, I'm not prepared to give you any reference, but let's say, I think that, well, actually there is more general formula which is given in Carmona's book. So as far as you rewrite your discrete Hamiltonian, the way that it produces your Markov chain, you are done.
Okay. Okay, thank you. Further questions? Oh, okay, let's end.